too quick. But today we're going to be talking about generative adversarial networks. I also think this is one of the coolest, at least the coolest visually representations of how machine learning works, and sort of really shows you how your model is learning. So we're going to start with some visualizations. So the first one you see here, you have an image on the left, and you're going to add in the style of the image on the right. So you're going to take this, style GAN, take the image of one image and add in the style of another image to create a brand new image. That's one really cool application. Sort of on that same thing, this one's called Gaugan. It's from NVIDIA. And what you can do is you draw something like the top 3 images. So you draw like a very simplistic pixel art kind of thing. And then you apply something to the left, one of those like style images, like a sunset or a different photo of a sunset with the sun in it. And what you get are brand new images that combine the two of them. So if you look in the bottom right, those 6 images are sort of created using this GAN model. And it's really, really incredible how it's happening, just creating these stunning visualizations. It also works with images. I'm hoping you can hear this image or this volume. Awesome. So I'm not sure if you could hear that. I'm really hoping you guys could. Well, it's worth a shot. So what that was there's these 2 people, and they didn't sing this song, or they were listening to a song, and so they didn't create this. The GAN model itself created them, moving their mouths and everything. I'm not going to replay this video, but if you guys want to check it out at the end, it's actually kind of funny. But GANs not only work for images, they work with audio, even though you can or audio and video, even though you can kind of see there's some distortions and they don't really look that realistic. So another application is this blank does not exist. I'm showing you 4 photos of a man, a cat, a horse, and a car, but none of these actually exist. All of these images were created using a GAN and aren't real. Like they were never taken as a real person. And if you look up "this person doesn't exist" on Google, you'll find an image generator that just constantly spits out new images of fake people, and they all look sort of realistic. When you look a little deeper though, you'll see that the model isn't truly creating a really accurate thing. Like if you try and think of the man as like, if you're trying to split him right down his nose, like most of our faces are pretty symmetric, but this guy has a lot more on his left than he does on his right. So it's a little unsettling, but this shows you how realistic an image again can produce is. Kind of on that note, the GANs aren't perfect. We're showing you sort of better things, but sometimes they mess up. For example, Putin on a horse becomes zebra Putin on a zebra. And then there's a lot of photos out there of really, really scary looking dogs and cats because your model isn't actually learning how to create them. It's just learning how to replicate what's in your data set. So let's start talking about how GANs actually work. Well, one more photo. GANs are constantly improving. Even if you look from 2016 to 2018, like they're getting so much better day by day, and that's continued into 2020. Also, shout out to the guy on the left. Ian Goodfellow was the creator of GANs, and he wrote a paper in 2013 titled GANs, and that was sort of how the field started. So let's get into how GANs work. In previous lectures, you've learned about neural networks as only one neural network, one that takes in some input and spits out some output. What a GAN does is it has 2 neural networks. You have a generator and a discriminator, and they're sort of playing a game against each other to sort of create a better image. So what that looks like is you take random noise, you feed it into your generator. It's worth mentioning here that your generator can be anything. It can be a recurrent net. It can be a feed forward net. It can be a convolutional net. It can be any one of those, but you'll feed it in some random noise. It will produce something. In this case, it's a convolutional network. And you get a fake image out of it. And then the discriminator takes in an image, either a fake image that's coming from the generator or a real image that's coming from a training set of real images. It'll look at that and then try and decide whether that's real or fake. So it's going to give you a score from 0 to 1, kind of like a logistic regression of how fake or real it believes what it just looked at is. So, for example, it'll look at this sort of dash from the training set, which could be a 7, could be a horizontal 1, and it'll say, that's real. Or it'll look at this 8 and say, that's fake, if it's a good discriminator. But if it's a bad discriminator, the fake image is going to fool it, and it's going to say, that's real. Here's the other analogy. So the generator is going to produce the Mona Lisa, a mediocre version, and a discriminator is going to say, that's clearly fake. But the next image the generator produces is going to be a lot better because it's learned to produce a better image. And though it might not be the exact same as the true image of the Mona Lisa, if your discriminator isn't good enough, it's going to say, that seems legit, it looks good enough, and it's going to give it a positive score or a score of that's real. And so there's sort of a game going on of the generator is going to improve itself and create better and better images. And the discriminator is going to improve itself and get better at detecting the fake images. And that's sort of the game that's being played to train your model. Again, the discriminator is going to be the exact same as your generator. It's also worth mentioning here that if you're working with images, we talked about just a feed forward convolutional neural network. So you start with a big image, and your convolutions sort of shrink the image, like with this discriminator on the right. Each convolutional net has a max pooling layer, which kind of shrinks the image and reduces dimensionality. But when you look at the generator, it looks like that convolutional net that you're used to seeing, but sort of in reverse. And so what you use instead of like a max pooling layer is you use an upsampling layer, which sort of expands the dimension of your image. So it'll go from like a 1 by 1 to a 4 by 4 and expanding the image. And there's a lot of thought that goes into that if you want to look into it more, but it's possible to do convolutions in both ways. Yeah, so your discriminator is kind of what we think of as a normal feed forward convolutional net, and it's going to output something as real or fake between 0 and 1, where 0 is fake and 1 is real. Your generator, let's talk about that a little more. What it's actually taking in is random noise. So you guys have used Python, like you're going to almost exactly feed it like Python or numpy.random.uniform or .normal. Like you're truly feeding it just random data. And it's going to transform that random data into something that looks like your image. And that's sort of what it's learning, how to take totally random noise and sort of like combine it and distort it in a way that it produces something real. So let's take a look at the actual math behind this training. At first, I know this looks kind of like a lot, but there's a lot of parts going on here. And I just want to sort of like really slowly walk through this because it will make all of our lives a little easier and help you guys really understand this. So first, what do we think the generator should do? The generator should produce images that fool the discriminator. So let's dissect what this generator training looks like and sort of get there. So we start with Z. Z is our random numbers. It's just like a big vector of random numbers. And what we're going to do is we're going to put it through the generator, which is sort of like, you can think of it as a function. So G of Z is going to be your fake image. And then D of G of Z is going to be what your discriminator thinks of your fake image. And so that's going to be a number between 0 and 1, and you're going to want to maximize it, which which is why you have this maximizing term. And you're not trying to maximize each one, you're trying to maximize the expectation. So looking at all of the possible random numbers it could be, let's look at all of them, sort of summing up all the different examples we see. Let's see how well we can fool the discriminator by by maximizing the value it outputs. So again, if the discriminator d of g of z outputs 1, that means it's a real image, and we're trying to maximize that. So a generator is trying to have it produce 1 as often as it can. Then we have our discriminator. So now we have two different terms. We have an x term and we have a z term. So our z term is almost the exact same, the term on the right. What you're doing is you're taking z, you're running it through g, so it produces a fake image, and then you're running it through d to then classify that fake image as real or fake. But we want our discriminator to classify real images, or we want our discriminator to classify fake images as fake. So we don't want to maximize how well it does. We want to maximize 1 minus how well it does. So in other words, the more real, it's going to be penalized for giving high scores that are closer to 1, and it's going to be rewarded for giving scores that are closer to 0, or it's going to be rewarded for accurately determining which ones are fake. And then when we look at the other term, we have x. Now x is from our real training data. That's like x is from p data. So that's looking at real data. We're going to take a random sample from our real data distribution or our real data training set, and we're going to see how our discriminator predicts on that. So we want our discriminator to predict 1 for that. So we want it to be a really high value because we want it to predict a real value or real image as real. So we're just maximizing that. If we wanted to instead maximize or minimize it, like maximize that it thinks that real images are fake, we would do the 1 minus trick, and that would make it try and classify all the real images as fake. But that's not what we're actually trying to do. That's just sort of how you can manipulate this loss function. And so this term here is telling you that your discriminator should do a good job of discriminating and deciding that real images are real. Were there any questions on that before I continue? I know this part's a little tricky. Okay, so what we've been learning about before is gradient descent. So that's sort of like, if you imagine you're on a hill, you're trying to go down, because most of the loss functions we've been looking at, you're trying to minimize them. So you're trying to go downhill to find the global minimum or the local minimum. And so you're using gradient descent. But here, you're trying to maximize two things. You're trying to maximize theta g, which are the same as the w, the parameters that you can change in your neural network. And you're trying to maximize theta of d, the discriminator parameters. And so instead of going downhill, now we're going uphill. And it works in the exact same way with a negative sign that's removed. So when you're going downhill, you go the negative of the gradient, you're descending it. But when you go uphill, when you're trying to ascend, you go uphill. So you have a positive thing. You go up the gradient as opposed to down the gradient.
I have a quick question. Regarding the math, like the expectation and maximizing it, or like not the expectation, but like the entire term. So is like the maximum for both 0? And if so, what is the minimum, like what is the range basically? What range of values can both of these like statements, terms take on?
I don't know exactly off the top of my head, but this isn't sort of what you think of as, this isn't exactly what you think of when we've been looking at other neural networks where it's like, there's one objective function, there's one loss function that you're trying to minimize. Here, there's two functions, and they're both kind of fighting each other. So both of them include both g and d in their objective functions and their loss functions. And they're both, when you change one, it's going to change the other. So you can think of it almost like a game, like they're playing against each other. So it's not useful to think of it in terms of like what's the range. It's more like they're both learning based off of these functions, which tell them what to do, but there's no like global maximum. They're trying to reach an equilibrium where they're both really smart, but there's no like perfect amount for each of them.
Right. I guess I just wanted to like connect this concretely to other loss functions we've seen. So like just looking at it separately, so only focusing on the generator, for example, right? The best case scenario is that the discriminator guesses 1, correct?
Mm-hmm.
So then it would just be expected value of log of 1, which is just 0, right?
Yeah.
But then the worst case scenario is that the discriminator guesses 0, and then the log of 0 is negative infinity. So I just wanted to like kind of, make it concrete with actual numbers to see like what range of values this takes on. And I just thought it was interesting that it's like it's basically negative. It's like from negative infinity to 0. And the same thing for the discriminator.
Yeah, absolutely. Great point. They're going from negative infinity to 0. Yeah, and so we're going to sort of look at it from a slightly different interpretation now. So what we're looking at here is like it's a loss function, and there's sort of a game going on. But now we're going to sort of shift a little and instead think of them in a more probabilistic way. And I should preface this by saying, like, if you understand up to this slide, you're going to be totally fine. The next few slides are sort of like jumping deeper into GANs. And if you don't understand it, that is totally fine, and you will not have any issue in life. But if you want to like read in a little deeper and sort of, especially if you want to read the actual paper, the Ian Goodfellow paper, and you want to like learn a little more about it, these next few slides are sort of how the actual researchers think about this problem. So we're going to start, and the first thing, I didn't write this on the slide. Now we're going to assume that our generator, or that our discriminator, is a perfect discriminator. So now, instead of it learning, we're going to say we've already trained a discriminator. So when it sees a real image, it knows that it's real. And when it sees a fake image, we know that it's fake. So in other words, we're sort of only focusing in on the generator. We're going to sort of take a deeper dive at the generator. We're going to look at it in a more probabilistic sense of looking at probabilities, because the generator is a function that takes in a random variable. So if you remember back on the slide, it takes in z, which could be a uniform random variable, or it could be a normal random variable, but it's some random variable. You're not sure exactly what it is. But what it's going to output is also going to be random, because it takes in something random. It does something deterministic, or it does something known within the whole generator, like it's a function of a random number. So it's going to produce something that's a random, number, or there's some probability distribution that it's going to produce. And so we call that P generated. It's it's the probability of what the generator produces. So like with the MNIST data set, like those handwritten digits, you can think of it as it takes in a uniform probability number between 0 and 10 or something, and what it outputs is an image, but that image has a 1 in 10 probability of being a 1. It has a 1 in 10 probability of being a 2. It's producing, so our function, our generator distribution, is an image, or it's a distribution over different images. That could be a 1, a 2, a 3, all the different types of all the different types of digits in the MNIST data set. And in the same way, we can think of the real data as a probability distribution. So sort of going back to that slide right here, these numbers in our training set can be thought of like, they can either be thought of like different images, which is sort of the way we've been thinking of them. Each of them are separate, but we could also say that like they're all part of the same distribution over digits that people have written hand by hand. So they're all part of some abstract probability distribution. And that's sort of like the biggest hurdle to get over, is to think of like these concrete examples of like a 1 as being a probability distribution, but it's going to allow us to do a bunch of work on what our generator is actually doing. So are there any questions about that? Can I explain that a little better? Because we're going to sort of jump forward using images as a probability distribution.
Yeah, I have a question, Ted. So is this probability distribution over all the possible digits, meaning it's going to learn what's the distribution of each class in your data set, or is it more in the pixel level? Like what's the probability distribution of pixel number 700 or something like that? And how does that relate to, I mean, like, yeah, conditioning on other pixels and that sort of stuff? I don't know if that's clear.
So yeah, that's a great point. We're looking at so like our data set is a 24 by 24 pixel image. So there's 768 total pixels. So we're looking at probabilities in a 768 dimensional space. So we're looking at each pixel as being either a 0 or a 1 as the space of our probability. So like you could get a random number for any of the 768 values. But what makes this problem possible is it's not this random noise that you're looking at here, because that's like truly random. There's some structure within those 768 pixels where the probability of getting this total gibberish is 0. It's very, very close to 0. And the probability of getting a coherent digit, whether it's a 4, a 1, a 7, those are going to be really high. So we're in a really, really high dimensional probability space corresponding to the total number of pixels. But our actual dimension that we're looking at, and the dimension, like the effective dimension of like how many true possibilities there are, is much, much smaller, because everywhere that the pixels don't create a coherent image, the probability of that is 0.
Yeah, that makes sense.
Awesome. So, like it's a hard thing. It's really hard to wrap your head around. It took me a long time, but we're now in this probability space where our real data is from some real distribution. It's some real distribution of our data, and our generator takes our uniform distribution or our normal distribution, our random number distribution, and it transforms it into a different distribution, which we're going to call the generated distribution. And so what we want is our generated distribution to exactly match the real distribution, because then our discriminator, which is still really good, is going to have no idea which one's real and which one's fake, because it only sees samples of that distribution. And if you give a really good discriminator an exact sample from either the generator or the real distribution, if they're the exact same, your discriminator can't figure it. Your discriminator will predict that they're real both times. So in other words, if our real distribution is the exact same as our generated distribution, we're going to fool the discriminator each time. And that's exactly what we want with our generator. If you go back and look at the loss term, what we want is it to be fooling the discriminator every time. And that happens when the generator distribution exactly matches the real distribution, or the generator, if we're going back to the concrete example, the generator exactly produces images that are the exact same as the real images. And so let's take a step back and sort of bring this down to a much easier level. How do you quantify the difference between two probability distributions? So this is like, if you have a normal distribution and a uniform distribution, how do you quantify the difference? And this is a question to you guys. How would you go about finding the difference between two probability distributions?
maybe one of the first things that might come to my mind is just taking the difference between the probability density at each point.
Let's, okay, how about graphically? If you want to look at a graph of a probability distribution, what do you look at? You were close, Spencer, on difference of areas under the curve. It's like one of the tools that you learn in like very basic visualization of data. How can you plot the frequency of different outcomes? You guys are getting closer. The exact answer I was looking for, you guys have it. It's the histogram. So to look at how often something happens, you look at a histogram. So these are both sort of normal distributions, roughly, and you take like 100 samples, in this case it's 200 samples or 800 samples of your distribution, and you plot what they actually equal to, and that sort of shows you your distribution. And so we have two different distributions. We have our blue and we have our green. And so now, if they were the exact same distribution, they would look the exact same. They'd have roughly the same number throughout all of them. Or they'd like have the same shape of the histogram. But if they're different, then you're gonna have like areas where the blue is a lot bigger than the black. Or that's, oh my goodness, those were two totally wrong colors. The green is a lot bigger than the purple, or the purple is a lot bigger than the green, depending on the differing probabilities and the differing probability distributions that these samples were taken from. And so that's sort of the idea behind how we quantify, how we like figure out whether a probability distribution is the same or different from another one. And to put that into a little more math, it's called the Kullback-Leibler divergence, and someone will correct me on how to actually pronounce that. But all you're doing is you're trying to, the divergence is another term for like distance or difference. And I mean, they're a little different mathematically, but they're all doing the same thing. They're saying, what's the difference between two distributions? Here we have pi1 and pi2, which are both normal variables. And you can think of this plot as sort of a histogram where they haven't filled in the bottom, or like it's just like a function. And all we're doing is we're sort of looking at each point and we're saying, how big is the difference at maybe x equals -1 or -2 on this graph? There's a difference between the two lines. So our difference, which is the KL, which is the green term, is going to be big. But then if you look just to the right of 0, where the two probability distributions output the same thing, they're going to be 0. The KL divergence is going to be 0 because the two histograms match up. They have the same amount at that point. And then in this case, because the KL divergence is not symmetric, it only looks at the difference between one and the other. You can have a negative value for the KL divergence, which is like your target one is going to be bigger or smaller than your -1 or than your other one. And so that's going to produce a negative or a positive number in the difference of your KL divergence. And that's almost exactly what you have in that equation up top. You're going to look at the sum over all x's. So if we go back and we look at our histogram, the sum over all x's literally means look in each of these bins. And for each of these bins, do something. What we're going to do, we're going to multiply the probability of getting that bin. So this is like a weighting term. Like if there's a huge difference in a bin that isn't used that much, like for example, out of 10, there's going to be a huge difference between the size of the blue or the purple and the green, because there is no purple and there's a lot of green, but we're going to weight it by the amount of green there is, because we don't want to make it too artificially big. We want to make sure that the differences that matter most are where there's more data. So we're going to weight it first by the probability of getting that, so the size of the histogram. And then we're going to take the log of our first distribution over our second distribution. So putting this in more quantifiable terms, if the distributions are exactly the same, if P of X equals Q of X, then you're going to get log of 1, which will be 0. So at that point, there is 0 divergence, which is exactly what we want. If they're equal, then you're going to have no difference. There's no divergence. If instead P is 2 times as big as Q, the difference is going to be 2, and you're going to get log of 2. So you're going to get a positive divergence, which says there is a difference here. Or if Q is 2 times bigger than P, you're going to get log of 1/2, which is a negative number. And so that's shown in the graph by any of the numbers between like 1 and 2 on this little plot. That's saying there's going to be some negative divergence. There's some difference, and it's the same as the positive difference, but it's going the other way. So instead of your first one, your P being bigger than your Q, now it's your Q is bigger than your P. So this is sort of the way that GAN researchers and everyone that uses probability distributions sort of quantifies how close two distributions are to each other.
I have a question. Could you remind me what happens when Q of X is 0?
When Q of X is 0, it goes to infinity. And that's an edge case that I haven't thought about. I'm pretty sure, I actually do not know exactly what happens for how they avoid that issue with the KL divergence, but maybe you can just.
Yeah, I also don't know either. This like just came to my mind. I've never considered that.
I'm guessing what they do is they cap it off and they say it's going to be, because it's infinity, like you just pick a really big number. Like say the maximum value you can have for your KL divergence is 100,000. And it's pretty obvious that if it's that big, the probability distributions are way out of line with each other and they're not close at all. And so this is sort of how we're going to approach quantifying whether our real distribution looks like our generated distribution. But we need to make a slight modification because the fact that this isn't symmetric is kind of an issue. So what I mean by not symmetric is that the divergence of P with respect to Q, or that P double bar Q, is not equal to Q double bar P. It's going to be similar, but all the negatives are going to be positive and all the positives are going to be negative because of this log term. And so instead, we use a slight modification called the JS divergence. And what the JS divergence does is it computes the average of the two. So this M here is the average of P plus Q divided by 2. It's like, let's take the exact middle of our divergence, or of our two different distributions, and we're going to call that M. And then we're going to look at the difference between P in that M and Q in that M. So instead of comparing one to another, now we're going to compare one to the average of the two and the other one to the average of the two. Sort of then both of those pieces will add up to be the difference between the two individual ones. So that the difference between P and Q is the same as the difference between P and M plus Q and M. But this has the added property that it's symmetric. So here, your values are always going to be greater than 0. If you look at this graph, you'll see P and Q, whereas before, when, let's call this red one, actually we can just look at red. When red is greater than blue, you have a positive KL divergence, and when red is less than blue, you have a negative. Now, when we look at this, we have red is greater than blue, and it's positive. But now when red is also less than blue, it's still positive. And so what it's pretty much doing is it's taking the absolute value roughly of the KL divergence. If you flip this part under the 0 line up and over, you pretty much get the JS divergence. And that's not exact, but you can sort of conceptualize it as that. It's sort of transforming it to always be positive and looking at the absolute value of the difference between two of them, as opposed to looking at just the true difference between the two of them. And so that's sort of how we're going to quantify the difference between two probability distributions. It can be shown, if you want to check it out, go check out the actual paper, the Ian Goodfellow paper. You can show that your loss of your generator, given D star, which is an optimal discriminator, is 2 times the divergence between your real and your generated distributions, your real images distribution and your generated images distribution minus 2 log 2, which is just sort of like a term that comes in with the math, but doesn't really mean anything. And so what we've gone from is this, these 2 different training terms that are sort of playing against each other. Now we only have one. Well, so also notice here, we're trying to maximize these 2 things. So we're trying to like go up the hill, create an ascent, and they're sort of playing against each other. So it's not obvious what the solution is going to be and what the best solution is going to be. But when we look at it in a probabilistic sense, what we get is a nice loss term where we're trying to minimize this loss term. There's a little fudging that goes on with assuming that your discriminator is perfect. But in practice, your discriminator trains much, much faster than your generator does. So it's kind of a good assumption that your discriminator can be thought of as the perfect discriminator. And you're only looking to really minimize the loss of your generator term. And so you get, so when your JS divergence, when PR exactly equals PG, you get DJS equals 0 because they're the exact same distribution, and you have a minimum of your loss function minus 2 log 2. But for any other values of PR and P where there is a difference, you get some sort of higher loss. And the other really, really nice thing about this is a linear function of loss. So it's not like a really complex boundary where you have to, or like even like a squared where you're not sure where the best value is. It's going to be linear. So you can sort of use some optimization tools that we know about to find the lowest value pretty easily. Yeah, so that's sort of like the end of the asterisks of the hard probability thought. Does anybody have any questions on that? All right, awesome. The final thing I want to talk about, okay, 2 more things to talk about. First one is called mode collapse. So this is when GAN training goes wrong. Unlike recurrent neural networks or convolutional neural networks, GANs are really, really, really hard to train. They're really finicky because instead of just feeding them images and labels, you're now there's like this intricate game going on between 2 different neural networks, and they're sort of playing against each other, and it's really hard to, and there's a bunch of added noise and randomness in there, so it's really hard to know what's going on in there. And so it's really hard for us to like give it a really good function and for it to learn exactly what we want to learn. So for example, we have our target on the right. This is what we want to learn. It's 8 Gaussian little dots. That's what we're trying to make it learn. And the top level is a good example of training. So it starts and it has, this is your generator output. It starts and they're all kind of here, like they're all random and centered at the middle because it has no clue what's going on. And then over time it spreads out, but then it starts to coalesce into the circle that we want. And then it refines itself and gets smaller and smaller. And you can see it learns the target distribution. It learns almost exactly what it should look like. So it's learned to mimic what the real value should look like to fool the discriminator. But our discriminator doesn't exactly know, our discriminator is also learning. So it doesn't exactly know what a perfect image should look like because it's still learning. It's still becoming a better discriminator. And so it might think that if you have any of these dots, only one of them or two of them, then that's still going to be a real image because those dots exist in the target images and those dots exist in the real training data set. And it has no way of knowing that you need all 8 dots for it to be a valid image. So what we're looking at in the bottom is called mode collapse, where it doesn't learn the full complexity of the distribution. It only learns a certain small part of it. And your generator, it's a lot easier for a generator to learn a small part of the whole image than it is for it to learn the whole image. And when your discriminator says, hey, that part fits into the real image, it might not be the whole thing, but it's good enough because it's definitely a part of the real image. Let's go ahead and say that's real. That gives positive feedback to the generator. And so it learns to just have 1 dot instead of the 8 we need. And as you can see, sometimes it'll change dots to keep fooling the discriminator. But what you end up with is instead of having 8 dots, you only have 1 dot. And that's called mode collapse, where your GAN produces something that doesn't have the same complexity as what you want. It doesn't have the same rich number of features. It kind of just produces like an oversimplified version that perfectly fools the discriminator, but doesn't fool it in the way we want. So that's just one of the many things that can go wrong with GAN training, but it's sort of like the easiest to see visually, and this is something you need to watch out for in your training of the GAN. Next, we're going to sort of look at this application, and I'm going to sort of explain how it's created. So what you have here is you have a man with glasses on the left, and then you're going to do some sort of addition and subtraction. So first you're going to subtract a man without glasses, and then you're going to add in a woman without glasses, and what you're going to get is a woman with glasses. So what you're doing here is you're saying man minus man plus woman and glasses without minus glasses minus glasses. So you get, so glasses stays the same. Glasses doesn't change, but you're sort of subtracting out the man and adding the woman. And so this seems like, how does this machine know how to do this? And this is sort of like one of the coolest applications of GANs. This is ability to like add different parts of it. And for that, we need to sort of talk about the latent space. So what the latent space is it's an abstract representation of the world we live in a smaller dimensional or a similar dimensional subspace. That doesn't really mean anything. But terms that are the same in our world are going to be close in the latent space. So man and woman, so when we did our I think it was classification lecture, we used word embeddings. And a word embedding is an example of a latent space. So if you remember, it was like 55 dimensions and it was just a bunch of gibberish numbers. But those two gibberish numbers, the gibberish number for man and the gibberish number for woman, in that 55 dimensional space are really close to each other. And they're a lot closer than man versus walking or man versus lion. They're close together and it's sort of like a representation of our world in abstract numbers that the computer can understand, where terms that are similar in the real world are going to be similar in this latent space. Radur, I'm not sure if you have anything else to sort of clarify the latent space. Or does anybody have the latent space?
No, I think you gave a pretty good explanation. I was just going to say, yeah, this is what we covered in the RNN lecture. So like before we could actually feed in the input, it just really helps to have some sort of representation for words. And like you said, the big takeaway here is like this similarity in direction between words. And just as a reminder, the embeddings we used were we mentioned glove and word to vec. And all you need to know is that these are like already pre-trained, like pretty good latent space representations. And if you remember what we did, or like especially at the intermediate or advanced groups, if you looked at the code, it's literally just a matrix. So you take the vector of the word, and just as a matrix applies a linear transformation to a vector, it does the exact same thing to your word, mapping it into the latent space. But yeah.
Exactly. So where we're sort of going with this is instead now, so before when I talked about Z, I was saying it was from some random uniform distribution. But now let's sort of play with our Z. Let's take the Z to be something meaningful to us and sort of say, we're going to start with man. We're going to say, instead of using some random number, we're going to use the random number associated with man. So again, it's just some like weird 55 dimension vector with a bunch of gibberish numbers between -1 and 1. So it's kind of the similar thing as a random number. And now let's take another one, which is woman. Another random sort of like meaningless number in our space, but has meaning to us. And let's sort of walk across between them two and see what the generator will give us. So when we go back and look at this example, man with glasses, what we do is we put that in the latent space. So that's some vector. And then when we subtract man without glasses, what we're sort of left with in our latent space is blank with glasses. So that's sort of like, I don't know, this is where it gets really hard to sort of describe, but it's like it's another random vector. And you can do vector addition on these things because they're just random numbers. It's the random vector that sort of means with glasses, and that's all it means. And then when you add in woman without glasses, you're adding the value of woman to it. And so now in your latent space, you have some random number that's equal to woman with glasses. Then when you feed that into your generator, it's going to give you women with glasses because it's been trained to take some random value and it's been trained to take some random value and spit out an image. And all we're doing is now we're tailoring what random value we give it to make an image that we want. So to sort of describe this a little more, we're going to watch a quick video. And the one difference that we have is before this was like a binary thing, like we're subtracting a full value and then we're adding a full value. But what if instead we subtract, we show the transformation between one to the other. So we sort of interpolate, we walk across the line from man to woman or from swimming to swam. If we like slowly trace across that whole latent space between those 2 points in the latent space, what do we get? We get something like this. And there's supposed to be no sound here. So this was trained on something called celebrity faces. So the real probability distribution that we're looking at is the distribution of all celebrity faces. Like there's some huge odd probability space that's out there that creates celebrity faces. And when we train our model, what we're doing is we're training our model to take in random noise and sort of produce something that's within the space of celebrity faces. And this is kind of like a weird thing to think about, that we're all just sort of like a sample from a probability distribution. And if any guys want to get really philosophical with me, like go right ahead, because we can talk about this more. But all we're doing is we're saying, let's take this distribution of known heads and now let's walk around in it. Like, let's see what different random values give us in our latent space and see what celebrity faces we get when we give it slightly different random values, slightly different noise. It's kind of scary, to be honest, because some of them look really, really gross, and some of them look exactly like a celebrity that you'd see on TV. So it's kind of crazy that our computers are getting this good to sort of model what we look like. And yeah, that's sort of what I wanted to leave you guys with, is the latent space is a really cool visualization tool and is sort of why GANs are so powerful. Any questions? If not, thank you for listening. And if you do have any other questions, feel free to shoot me a Slack DM or anything. I did GANs for a pretty long time over the last year, so I know about them. Yeah.
Thanks so much, Ted. You killed it. That was a really in-depth lecture. So we're going to have like a 3 to 5 minute break now, and you guys can start breaking out into your small groups.